Hello everyone, this is Edward from MATLAB Helper, and in this video we are getting in touch with a very important and useful toolbox. This toolbox is Simulink Design Optimization. Let's see how does it work and the different approaches that we are taking in order to learn the most important features of this toolbox. So, Simulink Design Optimization provides you some optimization methods in order to minimize a cost function. This toolbox is commonly used for dynamical systems as seen in control systems. This can help you to improve your system response and estimate parameters of your model. Regarding Simulink Design Optimization, this toolbox requires some mandatory products like MATLAB, Simulink, and Optimization Toolbox, and others toolbox which are related to this one, where we can find control systems, deep learning, and system identification toolbox. In fact, most of them will provide you help for linearizing systems, tuning controller parameters, and some optimization techniques. By the way, you could find out if you count with all of these toolboxes by typing VER in your command windows. So now the approaches will be introduced. First, we will use Simulink Design Optimization for estimating some model parameters, and in the second approach, we will see two different more examples to learn how the system response could be improved. Have you ever thought of creating a model and doing simulation through Simulink? Do you want to get your work done by blocks without writing even a single line of code? Simulink is widely used in automation, control theory, and digital signal processing for modeling and design. Learn with examples of the fundamentals level and become a professional in Simulink. Join our free online course on Simulink fundamentals and study at your own pace. Test your Simulink skills with the course certification quiz. So, for this first approach, we are using this model in Simulink, which includes two subsystems. The throttle system controls the flow of air and fuel mixture to the engine cylinders. There is a butterfly valve that opens when a driver presses the accelerator pedal. Opening this valve, and depending on the angle of this valve opens, the engine speed will increase or decrease. By the other side, we have motor subsystems, which models the input current of the motor and the torque applied to the motor. Even here we can find some parameters of this model. T, for example, is the torque applied by the DC motor. Theta is the angular position of the valve, represented by X in the model. T hard stop is the torque applied by the hard stop. J is the valve inertia. C is the valve viscous friction. K is the valve spring constant. So, in this first approach, we are finding like we have some real data collected from the system, and also this data will be compared with the data that has been previously simulated. So we will find that this data doesn't match, so the idea is to use parameter estimation app in order to do that real data and simulated data be the same. So let's start opening the model. For this, go to Command Windows in MATLAB and type this. Now you will see the model that has been shown previously. But now it's important to notice that once you open the model, this parameter will be uploaded. So you will see some model parameters like inertia, spring constant, and others one. Here will be important see that we have position 1, 2, 3, time 1, 2, 3, and input 1, 2, 3 data. This is important basically because when you do the estimating process, you will need some experiment values or data, and also you will need validation data. This is because experiment data will be for estimating the parameters, but then will be necessary compare the new response of your system with other real data in order to see if you have overfitted or underfitted the model. So now let's go to the model, and the first step will be go to apps and select this option. Now you will see something like this. So let's create a new experiment, and here we will have to add the output real data and the input real data. So for this case, for this experiment case, we will add time 1 and position 1 vector, and for the input, time 1 and input 1. Now we can plot this data that we have added. Okay, and now you will see the real data. Now you could be interested in to plot the simulated system response. Select this option and the response of your system will be plotted. So now you see that simulated and real data are not the same, and this is probably because the parameter that we have here in the model is not the true data or the true values. So also you will find that measured data is noisy. So before estimating the parameters, we will have to preprocess the data. So let's go to experiment plot, and the first thing that we are doing is extract the data. Let's say that we are only interested in the data between 0 and 0.5 seconds. Let's do enter and save as. Now we will have this new experiment, so we can delete or remove this one, and then we can plot again the new data. It can be done here in plot measured experiment data, or you can go to here and add the plot. So now the data is between 0 and 0.5. Next step is remove these exchange values, because these can affect the estimation process. So again, go to experiment plot and we select this option, replace data. Okay, now we have to select these unexpected peaks. Then go to replace selected data and select this option. So we are changing these values by let's say 90. So we have removed some of these values, but other values need to be changed too. We do the same for these values, and for this, and for this we replace the data by 86. Finally, these two values will be replaced by 15. Now you can apply the changes and you will have something like this. Now you could be interested and remove some noisy components of the signals. For this, again, in experiment plot, we can use a low pass filter. So we choose or select this normalized cutoff frequency, let's say 0.4. So we see that the data is very similar, and also you can choose the filter order, let's say 1, and OK. Then we apply the changes and close this. So now the real data looks better, so it could be a good idea try to estimate the parameters now. So let's select this, edit, and we will select the parameters that we are estimating. Let's say that we want to estimate J, C, input delay, and K. Okay. Okay. So again, we plot the model response. We have to see that this data will be selected for use it like experiment for estimation. We select this option, and now we can estimate. So the optimization method is starting, so you now will see some different graphs or plots. Here we have, for example, the estimation progress report, where you can find the iteration number of the method, of the optimization method, and also the cost function. Here you will see the comparison between measured and simulated data, and here in this last plot you will see the estimated parameters values for J, C, input delay, and K. So we have to wait until the optimization method finishes. You will see that once the iteration number is increasing, the cost function will be decreasing. So this is the expected thing, since we are choosing optimization method which computes the correct values of our model parameters. Now, once the optimization method finishes, you could think that all is done and the parameter has been estimated. But actually, we have to see if, or validate, sorry, if our parameter estimated are okay or not. So let's save the iteration. Now you will see here the estimated values of the parameters. And now we have to validate the data. So let's create two more experiments. Let's rename this as validation 1 and this as validation 2. Okay. And for the output, let's choose time to and position to data. And for the input, time to and input to. Let's plot this validation data and you will see this. Now we do the same for validation 2 with the difference that we are choosing other data, position 3 and time 3. And for the input 3 time 3. We plot. Okay. And now if our estimated parameters are okay when we plot the new model response for this validation data, and for this one the simulated data should be the same as this and this. Let's plot the model and we see that for both cases, validation 2 and validation 1, the data is not the same. So it's probably that we have overfitted the data or the model. So in order to correct this, you can go again to the experiment 1, edit, and you can be more restricted with the conditions for every parameter that we want to estimate. I mean, let's say that minimum value for all of these parameters are 0. Is to say, every parameter should be positive. And even let's say that the maximum value for input delay is 0.1. Okay, and we again do the estimating process. So the the optimization method has finished. We save the iteration and we can remove or delete this. It's time again to validate the data. Let's plot model response. And as you see, the validation data with simulated data for both cases remains different for each example. So for correct this, you even can go to more options, general options and optimization options, and you can improve your estimation by changing function tolerance, and parameter tolerance. Okay, and again we estimate. And we validate again the results. Other way or option to do the validation process is go to validation, select the experiment. Okay, and here you choose this and you validate. As you see, the data, the validation remains different to real data. We go again to more options and we change again these tolerance values. Estimate. Now our optimization method has finished. It's time to again save the parameters. We can delete this. And we can again do the validation process. Go to validation. select this, select experiment, this is okay, and we validate. Now, as you see, the validation data, is to say the real data measured, is the same as the simulated with the last parameter that has been computed. That in this case, they are called estimate params 17. The same for validation 2. So we can say that our parameters are correct, and you can see the new values here.
We assist from fundamentals to advanced MATLAB and Simulink projects, including IoT, artificial intelligence, machine learning, image processing, and many more. Our specialty lies in how we have assisted and provided guidance in academic projects and research work, as well as specialized training and workshops for MATLAB and Simulink. Our training programs are designed with the focus towards skill building and logic development, which involve a practical learning approach. Join our training program virtually or in office and improve your MATLAB skill set.
Okay, previously we have seen how to use parameter estimation app in order to estimate some parameters of a model. In this second approach, we are using other application of Simulink Design Optimization, and this is for response optimization. So depending that you want, you could use time domain requirements, frequency domain requirements, or even specify a tracking signal. In this case, for this approach and for this video, we are optimizing the response of a model using time domain requirements and specifying a tracking signal. There will be one model for using time domain requirement approach and other model for specifying a tracking signal.
Helper has proudly completed 1 year of monthly quiz contest. Our quiz of August 2020 is on Simulink. The first 5 winners between 11th to 20th August will get an e-certificate and featured in our winner showcase section. Participate in our free MCQ quiz, score 60% plus, and follow the quiz guidelines to be winners of this contest. Visit our website to explore all quiz contests.
So let's start with the second approach. For this, we are using this water tank step input model. So we are opening this model. This is a non-linear model with a PI controller that in this case we are using response optimization for estimating the correct values of this controller to get a better response. This response should be according our time domain requirements like overshoot and settling time. So let's see the model. Here we have the model of the tank. So this is non-linear. The output is the height of the water of the tank. And we have here some parameters like A, capital A, and B. A related to the cross-section area of the tank, and B and A for some constants related to the input and output flow of water. Let's run the code. And here we have the response. So as you see, this response contains a high overshoot since the steady state value is 2 and the peak value is approximately 2.4, and also this is a slow this is a slow response system because its setting time is about 35 seconds. So maybe we could be interested in improve these time domain requirements. So let me do small changes. First, we are changing this block. Let's use 1 as the final value. This is for some type of convenience. And let me go to MATLAB and change this value. Okay, and now let's change the initial condition to 0. And finally, ensure that the controller, the PI controller, contains these variables. So also is needed to initialize these values. One way to do this is go to modeling, model workspace, and here in the system that we are working, go to model workspace and create the variables, and then you can assign the value. Let's save. Okay, and now we are using a special block for response optimization, and this is check step response characteristics. This block should be connected to the output of the system since we are trying to improve this signal. The next step is open the block and specify your time domain requirements. Let's say that we want 1% of overshoot, setting time of 5, and rise time of 3. We do apply. Okay. Next step is go to apps and select response optimizer. This is the second app which is included by system design optimization. As you see, some black lines will be showing, and these black lines represent the condition, for instance, of overshoot, rise time, and settling time. Yes, since settling times was set to be 5, so these lines shows this condition. For now, we can plot the model response, and you probably will see that this response uh, don't match with the required specification. Now we have to add the design variables set, is to say the variables that we want to optimize. That in this case, these variables will be the controller PI variables, is to say this one and this one. Let's say that their minimum value is 0 for each variable. Let's do OK. And now we can optimize. Now you will see how the response of the model will be better. This is the initial response. This is the previous response. Now the blue one is the optimized response. We see how this response now is starting to complete or accomplish the time domain requirements. So the optimization has finished. This is the final function cost value. And these values are the optimized values for Ki and Kp parameters of your PI controller. So if we go now to the model, we save and run the code, probably the response will be the expected. So notice how the settling time is correctly about 5 seconds, and the overshoot is basically 0.
Are you looking for the implementation of a paper in MATLAB or Simulink? Have you tried different ways but still not able to proceed in your work? Are you looking for help in a long-term project or thesis? You have reached to the perfect place. At MATLAB Helper, we provide expert guidance with research assistance from one-to-one learning to full implementation of the work. Check all our amazing features and book your monthly plan today.
Finally, it's time to see the last approach, and for this example, as I mentioned previously, we are using other example. For this, we are using Radkin signal model that is very similar to the previous one. So we have this. In this case, we are using a PID controller. We add or put the variables that we want to estimate, these 3 variables, and let me initialize them using model data editor. Sorry. the model workspace. For instance, 0.1, 0.5, and 0.1. We save, we run the model, and we see the response. So, in this final approach, we are using a tracking signal as condition for optimizing the parameters of the controller PID. So, as you see, this is a great feature that other toolboxes or even blocks like PID, which includes auto-tuning methods, they don't include the possibility that you can specify the reference or the tracking signal. So let's go again to response optimizer. But in this case, after specify the variables that we want to optimize, and this one, we are not specifying time domain requirements like settling time, overshoot, or rise times, for instance, but we are specifying a signal tracking. So we choose this option, and here we have to do next. First, we remove or delete the signal, and here in specify reference signal, we are going to specify the the signal that we have to the system tracks. So for time vector, we can use linspace function. Let's say 0, 50, and 200. Sorry. And the amplitude would be given by 1 minus x minus t. That in this case, the vector t will be this. Now that we have defined the tracking signal, we need to specify the signal of our model that we want to be this. So we have to specify. So this is a message: no signals have currently been selected. Please go back to the model and click on a signal to select it. So we choose the output. We go again, and now we can select this signal. We click on OK, and now this will be the tracking signal or the reference that we want to get. We have already specified the variables that we want to optimize, in this case these ones. We can even plot the model response. So this is the actual response. The black one is the signal that we want. And now we can optimize and see how the response of our model is being this one, and you will see how this parameter change. So as you see, finally the optimization has finished. These are the new values for the controller parameters, and here we have the response of our model that in this case is the blue line. So the optimization was done, and it was done correctly. So with this example we finish this explanation about Simulink Design Optimization. We have seen two different approaches, one for estimating parameters of a model, and other that is very similar to the first, with the difference that here in the second one we was estimating controller parameters. And also you have seen that to get some response of your model using response optimizer, you can specify time domain requirements or even frequency domain requirements. And more than this, you can even specify a tracking signal, and these are important to know that these features uh, are not included in other toolbox or Simulink blocks. So because for this toolbox is very important, useful, and even could be used for other approaches, like for example, let's say you want to find some parameter gains for the case of space state control using Paul's assignments method. So this is only idea, and you can even try this. So thank you for watching this video. Do like this video if you found it helpful. If you have any query, post it in the comments or get in touch with us. Follow us on LinkedIn, Facebook, and subscribe to our YouTube channel. Education is our future. MATLAB is our future. Happy MATLABing!
Hi, I am Abhishek from MATLAB Helper. I want to thank you all for participating in our webinar, quiz and courses. We are doing a series of 5 webinars followed with live interactive session. I am hosting a webinar on 2D mapping with Arduino and ThinkSpeak on 15th of August. 5 best comments from my webinars or live interactive sessions will be awarded with free access to one premium course and certification on completion. Join me to learn about installation of various hardware packages in MATLAB, programming the Arduino for the ultrasonic map maker, and data visualization over the ThinkSpeak. Know more by visiting my webinar page. And test your Arduino skills by participating in our free webinar quiz.